The SVD, the most useful factorization in all of applied math. Every matrix is rotate, stretch, rotate. A matrix is just a grid of numbers. Look at it, and you cannot tell what it does or which parts matter. The SVD pulls any matrix apart into a few simple patterns, ranked from most important to least. Throw away the unimportant ones and you compress images, clean up noise, and power recommendations. That is the whole payoff. But what does that even mean? Start with a circle. Eigenvectors cracked open square, well-behaved matrices. But most matrices out in the world are not symmetric, not even square, and eigenvectors quietly give up on them. Picture the giant table a streaming service keeps. Every user down one side, every movie across the top, almost every cell blank. It still predicts what you will love, and by the end that prediction comes straight out of the picture we are about to draw. The SVD never gives up. Here is the unit circle, every direction of length 1 and 2 perpendicular directions on it, V1 and V2. Now apply the matrix. The whole circle stretches into a tilted ellipse, and those two directions land exactly on its axis. That always happens. For every matrix, the circle becomes an ellipse, and the lengths of those two axes are the singular values, here about 3 and 1.5. Find those directions and those two lengths, and you have taken the matrix apart. It is forced to be an ellipse, never a lumpy blob, because all a matrix can do is rotate, stretch, and rotate, and none of those can bend a smooth oval into anything stranger. The long axis is the first singular value, the short axis the second. Singular values are just how far the matrix stretches along each axis. So the matrix is secretly doing three simple things in a row. So how does a plane matrix turn a circle into a tilted ellipse? In three simple moves, and the SVD is exactly those three moves written down. This is the matrix we have been applying all along. Just 4 numbers. On its own, it looks like nothing. Watch what it is secretly doing to space. First, V transpose, a pure rotation that spins the two special input directions onto the plane X and Y axes. Then S, stretch along X by sigma 1 and along Y by sigma 2. This middle step is the only one that changes any lengths. Finally, U, another pure rotation, spinning the stretched axes to the ellipse's final tilt. Chain those three together and you have rebuilt the matrix. A equals U, S, V transpose. 2 rotations with a single stretch in between. That is all any matrix, of any shape, ever does to space. So there it is. Let us name the 3 pieces. Now name the 3 pieces of A equals U, S, V transpose. U is the output rotation. Its columns, the left singular vectors, point along the ellipse's axis. S is the stretch, and nothing else, just the singular values down the diagonal. Biggest first, and never negative. They are the lengths of those axes. And V transpose is the input rotation. Its rows, the right singular vectors, are the perpendicular directions that get mapped straight onto the axis. And those 3 pieces act on a vector in one clean line. One identity is the whole SVD. To feel what is new, set last lesson's equation beside it. Last lesson, eigenvectors. A scales a vector along its own line, the same direction in and out, one basis doing both jobs. Powerful, but it needs a matrix with enough eigenvectors, and most matrices do not have them. The SVD loosens exactly one bolt. Let the output use a different basis from the input. A sends each right singular vector V to sigma times a matching left singular vector U, a direction in, a different scaled direction out, 2 bases instead of 1, and now every matrix complies. Geometrically, the perpendicular V's on the unit circle land exactly on the perpendicular axis of the ellipse, each stretched by its singular value. Everything else in this lesson is that one line, unpacked. Hold on to it. A V equals sigma U is the SVD in a sentence. One theorem does the heavy lifting. any symmetric matrix S, one that equals its own transpose. Factors as Q lambda, Q transpose. Q is a rotation whose columns are perpendicular unit eigenvectors, so Q transpose Q is the identity. Lambda is diagonal, just the eigenvalues, and the spectral theorem guarantees they are all real. For A transpose A, they are never negative either. And Q transpose undoes the rotation, so a symmetric matrix does nothing but stretch along those perpendicular axes. That is the exact form we match A transpose A against next. This is the one outside fact the SVD rests on, and it always applies because A transpose A is symmetric for every matrix A. But where do U, S, and V actually come from? U, sigma, and V are not new magic. Let us derive them, assuming nothing and skipping nothing. We want U, sigma, and V. We do not yet know they exist, so assume they do and see what that forces. Form A transpose A and substitute the assumed decomposition. Transposing a product reverses its order, so the two U pieces end up side by side in the middle. U is a rotation, so U transpose U is the identity. Sigma is diagonal, so sigma transpose sigma is sigma squared. What survives is V sigma squared V transpose. Now the one outside fact, the spectral theorem from last lesson. A transpose A equals its own transpose, so it is symmetric, and the spectral theorem promises every symmetric matrix factors as Q lambda, Q transpose, Q a set of perpendicular unit eigenvectors, lambda its eigenvalues, all real and never negative. We derived one factorization. The spectral theorem hands us another, and a symmetric matrix has only one. Both are an orthonormal matrix, then a diagonal, then that same matrix transposed. So they must agree, piece for piece. Matching them, V must be Q, the eigenvectors of A transpose A, and sigma squared must be lambda, so each sigma is the square root of an eigenvalue, real, because the spectral theorem keeps every lambda non-negative. Not a guess, the only thing they can be. And A transpose A is symmetric for every matrix A, square or rectangular. So the spectral theorem always applies and always hands us V and the singular values. We have V and sigma. Now build U and check the whole thing holds. We want the action form AV equals sigma U, so define U as AV scaled back by its sigma. Check the length. AV dotted with itself is V transpose A transpose AV, which is lambda. So AV has length exactly sigma, which makes each U a unit vector. Between two different U's, the same move gives 0, because the V's are perpendicular. So the U's are orthonormal and U is a rotation. For free. By construction, A sends each V to sigma U, and since the V's are a full basis, that pins down what A does to every vector, which is exactly U sigma V transpose. The construction works, so the SVD exists for every matrix, no exceptions. That is why it never gives up where eigenvectors do. A transpose A is symmetric for every A, square or rectangular. So the spectral theorem always applies and the SVD always exists. No matrix is ever defective for it. Definitions are slippery, so let us actually compute one. Let us grind out a real SVD on a matrix that is not even square, a 2 by 3. Nothing skipped. Here is the matrix. 2 rows and 3 columns. Multiply A by its own transpose. Whatever shape A was, this comes out a small square matrix, here just 2 by 2. Its eigenvalues are 25 and 9, the same trick as last lesson. Take square roots, and the singular values are 5 and 3. The eigenvectors of AA transpose are the left singular vectors U, along 1, 1 and 1 minus 1. Push each U back through A transpose and scale by its sigma, and out come the right singular vectors V. Stack them up and multiplying it back out returns the original A exactly. And for a symmetric matrix, this collapses to the plane eigendecomposition. So the SVD really does contain last lesson as a special case. But the input space was 3-dimensional. We only used 2 directions. The inputs lived in 3 dimensions, So V has a third column we never used. Watch what the matrix does to it. Complete the basis. The missing V3 is the one direction perpendicular to the first two. Push it through A and it collapses to 0. The matrix annihilates that whole direction. A 0 output is a 0 singular value, the very same crushed direction we met as a 0 eigenvalue last lesson. And that splits the singular vectors into 4 meaningful groups. Split U and V at the rank, the number of non-zero singular values, and they hand you every subspace anyone ever asks about. The right singular vectors with non-zero sigma span the row space, the directions that actually go somewhere. The ones with 0 sigma, like our V3, span the null space, the directions crushed to 0. On the output side, the left singular vectors span the column space, everything A can reach, and the leftovers span the left null space. One decomposition, and all 4 fundamental subspaces fall out, orthonormal and sorted. One more piece of bookkeeping before the payoff. A quick word on shapes, because the worked example quietly used a shortcut. In the full SVD, U is m by m and V is n by n, both complete square rotations, and sigma is the same shape as A, but only IR of those singular values are non-zero, where R is the rank. Every column of U and V past the R teach gets multiplied by a 0, so it does no work. Drop the dead columns and you get the thin SVD, just the first R of each. It still rebuilds A exactly, with nothing wasted, and that is the form we actually computed. So when U looks m by m in the definition, but 2 by 2 in the example, that is the full versus the thin SVD. The same decomposition with the zeros trimmed off. Now the reason anyone actually reaches for this. Here is where the SVD earns its fame. And it starts from the same A equals U sigma V transpose we already built. We just regroup it. We have A as 3 matrices. Watch what happens when we multiply them out a particular way. Here's the one fact. Any matrix product is also a sum, each column of the first times the matching row of the second. A column times a row is a rank 1 block. Apply it here. The columns of U sigma are the U's scaled by their singular values, and the rows of V transpose are the V's. And the product turns into a sum, a stack of rank 1 layers, one for each singular value. Not a new decomposition, just U sigma V transpose regrouped. Take our worked example. With singular values 5 and 3, A is 5 times the first layer plus 3 times the second. Add those 2 layers, entry by entry, and you land exactly on the original A. The layers really do rebuild the matrix. The layers come pre-sorted, biggest sigma first, and the matrix's energy is the sum of the squared singular values. So the first few hold almost all of it. So keep the top K layers and you get the best possible K-piece approximation of A. The Eckhart and Young theorem. You do not search for the best summary, you take the top layers and stop. Throw away the small singular values and you lose almost nothing. And that one idea compresses your photos. A photo, to a computer, is just a grid of brightness numbers. So it is a matrix, and we can take its SVD. Here are its singular values. Biggest first. The full image keeps everyone. Keep only the single biggest layer, and the whole photo is just broad bands of light and dark. One singular value out of hundreds. Add 2 more layers, and the brightest shapes appear. The sun and a hint of the hills. Just 8 layers, and you already recognize the scene. At 16 times less data than the full image. 20 layers, and the surface texture fills back in. You would be hard-pressed to call this a copy. By 50 layers, it is essentially the original. And the layers we dropped were only the faint singular values at the tail, fine detail and noise. So compression is not magic. It is just keeping the big singular values and throwing away the small ones. The exact rank K approximation from a moment ago, now you can see it. Now collect that promise from the very start. Now collect the promise from the very start, the streaming table that was mostly blank. Lay the streaming data out as a matrix. 1 user per row. 1 movie per column. Almost every entry missing. The goal is to guess the blanks. Here is why the SVD has a right to an opinion. Taste is not 1,000 whims. It runs on a few hidden dials. Gritty versus feel good. Indie versus blockbuster. That is just saying, the table is low rank. So truncate to a few layers. Each left singular vector U scores every user on a hidden dial, and each right singular vector V scores every movie on that same dial. A predicted rating is just how well a user's dials line up with a movie's dials. A weighted dot product. The SVD discovered those dials by itself. Nobody labeled them. One honesty note. Real systems use a close cousin. Regularized matrix factorization. Fit to only the ratings people actually gave. It is the same low-rank idea adapted to missing data. And it is what won the famous Netflix prize. And if this all feels familiar, it should. You have already met the SVD in disguise. Let us derive PCA from one question. Which direction does the data spread out the most? Center the data, pick a unit direction V, and project every point onto it. The spread along V is the average of those squared projections. Here is the one trick. A squared dot product is a little quadratic form. V on the outside, an outer product in the middle. Pull V outside the sum, and the middle is the covariance matrix C. So variance along V is just V transpose CV. That is where C comes from. It turns a direction into a variance. PCA wants the direction of most spread, so maximize V transpose CV, but only over unit vectors. Or you could cheat by lengthening V. Handle the constraint with a Lagrangian, subtracting lambda times V transpose V minus 1, which is 0 exactly when V has length 1. Take the gradient with respect to V and set it to 0. 2CV from the first term, 2 lambda V from the constraint. The 2's cancel and it becomes CV equals lambda V. The best direction is an eigenvector of C. Its variance is lambda. So PCA is exactly the eigenvectors of the covariance matrix. Every principal component is an eigenvector of C, and every eigenvalue is the variance along it. But forming C and eigendecomposing it is the slow road. The SVD is the shortcut. We need the eigenvectors of C, 1 over n times x transpose x. Watch what the SVD of the data does to it. Take the SVD of the data matrix itself. X equals U sigma V transpose. Plug it into X, transpose X. Transposing the product flips the order so the two U's meet in the middle. U is a rotation, so U transpose U is the identity, and the inner rotation cancels. Sigma is diagonal, so sigma transpose sigma is sigma squared. What survives is V sigma squared V transpose. Divide by n, and the covariance matrix has factored itself into V, a diagonal, and V transpose. But that is an eigendecomposition. So the principal components are the right singular vectors V, and the variance along each is sigma squared over n. PCA falls straight out of the SVD of X, and the ranking lines up. Keep the top principal components, keep the biggest singular values. The same truncation as image compression. In practice, nobody builds C at all. Squaring X into X, transpose X, loses precision. So you run the SVD straight on the data. PCA was the SVD all along, and it quietly solves the most common problem in applied math. Here is arguably the single most used thing the SVD does. Solve AX equals B when there is no exact answer. Usually AX equals B has no exact solution. A tall, skinny A with more equations than unknowns. So we settle for the closest thing. Find the X that makes AX as close to B as possible. That is least squares, the backbone of regression and curve fitting. The SVD hands you the answer. Build the pseudo-inverse, A+, by flipping the decomposition around, V sigma plus U transpose. Sigma plus just inverts each non-zero singular value, 1 over sigma, and leaves the zeros as zeros, so you never divide by nothing. Then X hat equals A plus B is the least squares solution. And because you only touched the non-zero singular values, It is the numerically stable way to get it. Every linear regression, every overdetermined system, leans on this. It is the SVD's workhorse. And the singular values warn you when that solve is fragile. Two singular values, the biggest and the smallest, mean a lot on their own. Picture the ellipse again. The longest axis of the ellipse is sigma 1, and that is the most A can ever stretch a unit vector, so sigma 1 is the matrix's gain, its operator norm. The smallest non-zero singular value, sigma r, is the least it stretches along any direction it does not crush, the shortest axis of the ellipse. Their ratio is the condition number. When it is huge, the ellipse is a thin sliver, and tiny errors in B blow up in the answer. It is the one number that says whether a computation will hold its precision. A near zero smallest sigma is exactly why the pseudo-inverse drops the zeros instead of dividing by them. From photos to data to the web, it is one decomposition. Search and topic modeling take the SVD of a word by document matrix. Latent semantic analysis is literally that, and documents that share no words can still come out close. Recommendation engines factor a giant ratings table into a few taste factors. The same low-rank trick from the blank table chapter, Netflix style. Cleaning noisy data is just dropping the small singular values, because the noise spreads itself across those tiny last layers, while the signal sits in the top few. And squeezing high-dimensional data down to its few most important directions is just PCA, which we now know is the SVD in disguise. So, the whole idea in a few lines. Every matrix, of any shape, turns the unit circle into an ellipse, and it does it in three moves: A equals USV transpose, a rotation, a stretch, and a rotation. The singular values in S are just the lengths of that ellipse's axis, how much the matrix stretches each way, and splitting U and V at the rank hands you all four fundamental subspaces. Keep the big singular values, drop the small ones, and that blank streaming table from the start is no mystery. It was low rank all along, a few hidden taste dials wearing a million cell disguise, and the SVD is the tool that reads them off. That is the singular value decomposition. Every matrix of any shape is a rotation, a stretch, and a rotation. USVT.